Hey all, welcome back. Module 11. Wow, and this is chapter 15. So the penultimate chapter. And in fact, in this week, we will cover both chapter 15 and 16. And I'm also going to sneak in a little bit of something that's not in the textbook, just because in my mind, there's a glaring omission in the textbook. It seems to suggest that the dominant field right now is cognitive psychology. That seems to be where it leaves you. I think that's a few years out of date, to be honest. I think, neuroscience and cognitive neuroscience and social neuroscience and everything neuroscience is the current paradigm. We'll talk about paradigms a little bit. And so I just want to talk a little bit about that too, and also bring in a little bit of data mining to get you thinking about where that might fit in the psychology of the future. But that's getting ahead of myself. Let's go here to Module 11A. And so this is going to relate to Chapter 15. And the way things are looking for me, because of something I want to do to you in this lecture, I think what I'm going to do with Chapter 15 is maybe just have two longer videos, 20 minutes to 30 minutes. Just because it seems to work best for the organization of things. But with that in mind, let me go a little more quickly and let me see if we can make this not too long. I do want to start here. Weird little place to start. But I would like you guys to look at these words, and without writing them down or taking a picture of them with your camera or anything like that, just use your mind. Look at these words and try to remember them. I'll give you a little bit of time to do that. If you'd like, of course, just press pause and do it for longer. I'm not going to stay here too long, but you can pause as long as you want. Okay, so we're going to come back to that. That's for actually the end of the lecture, but I just want to throw those out there. You've studied them all, and you're trying to remember them. Okay. So now let's get into the lecture itself. And the textbook takes a bit of an odd mix. You're going to find, as we get into cognitive psychology, which is what we're going to move towards here, you're going to find that we get a real mixed bag of things. And so I'm going to try my best to kind of connect these things and let you understand, why they're relevant. And one of the relevances really goes back to humanistic psychology. Remember, they call themselves the third force. And they said, psychoanalysis is out there and behaviourism is out there. There are two very strong camps, but the humanists didn't really like either one that much and thought there needed to be a third force. It's unclear that humanism became that third force, but it seems like cognitive psychology did. And so that's, where we kind of start, which is once again with a sort of pushback against behaviorism. So cognitive psychology is going to be an interesting mix of some of the things we've talked about. So the first one is that logical positivism, that embrace of experiments and statistical analysis. When you took intro psych with me, probably, chapter 2 of that textbook is called research methods. And we teach you those research methods as though this is the way we all do psychology now. But if you now, having seen, this course and gone through this course, you realize that there's all sorts of ways people have done psychology, right? From just sort of sitting and thinking and talking, William James, to introspection, to phenomenology, to people like Kohlers who just said, look, that ape suddenly saw the light. They had an insight. People use so many different methods to try to get at minds and how they work. But it now sounds like logical positivism is the way we do things. And that's largely because of the adoption that cognitive psychologists had. So these are going to be very experimentally minded people, but people who find behaviorism a little too restrictive. That it defines psychology so strictly and it excludes so much of psychology. And these are people who started to say, no, I don't think we need to exclude so much. And so let's start that discussion here a little bit with Chomsky. So for example, Chomsky looked at the way behaviorists focused on language, and he thought any psychology of the human experience had to include a theories of language development, because it's probably the thing that most differentiates our species from so many others. The way we use language so flexibly, it allows us to transfer learning across space and across time in a way that no other animal species can. And so if we really want to understand the human experience, we have to think about language. Now, the behaviorists had thought about language. And so when they thought about a child growing up and had the question in mind, how does a child learn to use words in an adult way? What they said was, of course, it comes down to rewards and punishments, so that the child would hear something or want to express itself and would utter certain things. When it uttered the right things, when it said the right words at the right time, we would praise it, maybe explicitly or maybe just implicitly by giving it what it wants, right? So if it asks for something clearly and we understand it, we can give them what they want. If they use words inappropriately and we don't know what they're saying, then there's a friction that we could call punishment. It's not like slapping them or something like that, not that kind of punishment, but it's like the kid wants a pickle and they can't say the word pickle and they say, I don't know, I didn't want to try, but they say something that you don't understand, and then they're not getting their pickle, right? And so that's kind of could be frustrating for them. So this is what the behaviorists thought, is that slowly over time, based on the rewards and the punishments, that children learn to say words in the right way. Now, Noam Chomsky, as a young student, looked at this explanation and thought, no, that's not right. He believed that our use of language, and I'll show you some examples in a moment, was very, very flexible and could not be described as we learn how to do the right response to the right stimulus. He said, in fact, we can deal with brand new novel things that we've never seen before, and we can kind of understand them. And I'll show you some examples. But he thought language was much more dynamic and much more flexible, and that we needed a better theory to understand them. Interestingly, he argued for this notion of a universal grammar, as you see in his book. This isn't his book, this is V.J. Cook's book, but focused on Chomsky's notion of a universal grammar. So this is going to be the controversial idea from Chomsky. He's going to go all the way back to Descartes. Well, not all the way back to Descartes, but he's going to start talking about what Descartes would have called an innate idea, something you're born with. And he thought we were born with this sense of grammatical structure, what he called a universal grammar, and that when we were learning language in our context, what we were kind of learning is which language we're exposed to. We have this sort of universal grammar that we can now tie to any language in our environment. And so when we have a specific language in our environment, then what we're doing is sort of populating our universal grammar with this language. But he thought the universal grammar was there already. Okay, so we'll talk about all of this in a little bit more detail, but one of the interesting things from the Chomsky approach is this, when we talked about Ixiom's wheel, do the same ideas come and go and come and go? We've talked about things like innate knowledge, all the way back to the earliest philosophers, but including people like Descartes. And then we talked about, that becoming sort of more like genetic, not sort of innate knowledge, but rather, things you may have inherited genetically. And so we started talking about nature versus nurture, but in that case, nature was more genetics than it was innate. You were born with it. And then, of course, the behaviorists really said, hey, nurture, 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 let's focus on that. And now Chomsky's coming back to innate knowledge. So Ixiom's wheel, huh? So let's talk about this a little bit more. So really his argument is based on this idea that language, we can use language in a creative and flexible way that he didn't think you could explain just by certain utterances being rewarded or punished. So here's some examples he gave. If you gave people these two sentences, colorless green ideas sleep furiously, or furiously sleep ideas green colorless, he said neither of them makes any sense at a meaning level, but the first one feels right. The second one does not. Or you could say the first one feels better. And so he said, we all have this ability to reproduce and recognize grammatical utterances, things that fit a sort of grammatical structure. And he thought this grammatical structure was what he called autonomous and independent of meaning. So it doesn't require meaning. These things don't mean anything. Neither one of them does. But the first one feels grammatical, the second one doesn't. So it conforms to some structure that's independent of meaning. And this is the structure that he thought was innate, that we were born with, right? So here's another notion that he says. We can't just use rewards because language is so context dependent. It's very ambiguous. And the grammar is allowing us to figure some of this ambiguity out. So here's two examples. Time flies like an arrow. Fruit flies like a banana. He said, pretty much the same thing. But when you look at these two utterances, flies is treated a little differently. Usually with time flies like an arrow, we see flies as a verb, right? It's flying like a bird. Fruit flies like a banana. Here we're usually saying, these are those little fruit flies. So now it's a noun, right? It's a kind of fly we're talking about, a fruit fly, and they like bananas, and we do sometimes see fruit flies around bananas, right? And so this word flies could be a verb or could be a noun, and it's the grammar that tells you which. So, just being rewarded to say flies for flies is not enough of an explanation, because we have to get at, what that word means to you. And that same stimulus can mean very different things depending on the company it keeps, depending on what role it's playing within this universal structure, this universal grammar. And so, he thought you needed that to be able to explain our use of language. He also talked a lot about surface structure and deep structure. And this is where, the stimulus is just a surface thing. But he said, no, language is not just a surface thing. The ambiguity shows us that already, that flies can mean different things. And any sentence can. You take a sentence like this one, the shooting of the hunters was awful. What does that mean? In fact, it can mean different things, right? So first of all, the surface structure is just the words. The shooting of the hunters was awful. This is the surface structure. The deep structure is what it means. To understand this, we probably need even more context, because this could mean that the hunters were terrible shots. This could mean that the hunters were shot, and that was awful. This could mean that the hunters shot something that was awful. Maybe a bunch of hunters shot an elephant, and we can say, wow, the shooting of the hunters was awful. So, it really means at least three different potential things here. How do we know what it means? Well, this sentence would occur in a larger paragraph, and that would disambiguate it as well. But this is what the role of grammar is, especially in contexts like this, that the grammar allows us to go from this surface structure and get at the meaning of that. And again, Chomsky said, behaviourism just can't explain this. And he thought the only way you could explain it was a universal grammar. Now, this is pretty recent, right? And so we used to think innate ideas and all that, the cave, the analogy in the cave, those are relatively ancient ideas. And now we have somebody, in the 60s proposing an innate idea that we're born with. And so it was a little controversial. It got a lot of attention. And one of the things I don't mention here, by the way, and I should have, there's a movie called Chomsky you can find. Chomsky is a chimpanzee that they tried to train language to. So they named him after Nim, just to make this connection, and kind of saying, does a chimpanzee have this universal grammar? If it's treated in a human enough way and uses maybe sign language rather than words, could it nonetheless show this evidence of, shallow surface structure and deep structure, and could it actually get that sort of rich use of language like humans have? Okay, just to give you a little bit of a connection. So if you're ever bored, check out the movie Chomsky. By the way, it has a former UTSC prof in it. You can check that out. So Yeah, this is so he talked about what he called Cartesian linguistics. So linguistics is the study of words and how they are used. Noam Chomsky was definitely a linguist, and he came up with this idea of Cartesian linguistics, and he calls it Cartesian because he's directly linking to that idea of innate ideas. So, which Descartes, also talked about. So, it let's just read it. The central doctrine of Cartesian linguistics is that the general features of grammatical structures are common to all languages and reflect certain fundamental properties of the mind. There are then certain language universals that set limits to the variety of human language. Such universal conditions are not learned. Rather, they provide the organizing principles that make language learning possible. So he thought these universals, like the universal grammar, were sort of a reflection of the system that we have available to us, and it set limits on what our communications were able to be, but it also provided structure that allowed us to actually learn languages. He also thought these were universal. So he thought that a child born in China and a child born in Canada would have the same universal grammar, and it's only through interaction with their language that they might tweak their word use to be more Canadian or more Chinese. But at the fundamental level, they start in the same place. So a very sort of powerful idea. How does it fit in the chapter? Well, because it was, again, one of these cracks in behaviorism where they started to say this is something that behaviorists just can't describe because they've limited themselves too much. And yet in Noam's view, there were examples that showed you had to get to this level if you really want to discuss human behavior. And so it was really showing the limits of behaviorism. Okay, so now let's just talk a little bit about why behaviorism was so limited, and why the next thing I'm going to show you kind of blew that out of the water a bit. The claim of a lot of behaviorists was that the only things that are sort of solid enough to be considered scientific are the things that you can directly see, like stimuli and responses. And so therefore you had to focus on that. And that things like consciousness or memory or attention or whatever were just too fluffy. They were like, what the heck do we mean by all that? That's not scientific talk. Stop talking that way. Well, they were fluffy. People didn't really know what memory meant, like how a memory system would actually work. What do we mean by attention, etc. And until something came along that really started providing a very clear analogy. Now, what's that thing? It is this thing: computers. So first built by Alan Turing as a device to crack coded transmissions during World War II. There's also a great movie about that. I should know the name of it right off. Fascinating on multiple levels. Turing was a genius. He did all sorts of amazing things that we'll talk about. Building the first computers is pretty much up there. He was also a homosexual at a time when homosexuals were treated horribly. So the movie, whose name I'm blocking on right now, but it kind of talks about both of these sides of Turing, and it's an interesting movie. I highly recommend it. Okay, but Turing built this, and it really helped a lot of people say that the Allies won World War II, perhaps because of Alan Turing, because his machine was able to crack a bunch of codes that were used to code transmissions that the Nazis were sending. So once we could crack those codes, I say we because Canada was on the side of the Allies, once we could crack those codes, we could intercept their communications, and that was very important for ultimately beating them. When you know troop movements and stuff like that in advance, and you can anticipate them, then you can do some nasty things. So may have helped to win the war, important person. But he also created this thing that became a powerful analogy, almost like how chemists and thinking about atoms kind of looked at the solar system and thought, hey, maybe we can think of the atomic structure in the same way as planetary structure. People started to look at computers and they said, well, wait a minute, these computers, they're accepting input from the world through their keyboards and mice, and now you can just talk, right? And they hear that input, even more human-like, you'd say. So they take that input, they process it, they store some of what they process, they maybe connect it with other information they have. Now with the internet, of course, they can connect it with all sorts of information from around the world, and then they ultimately output the product of their processing. And they'll use screens, printers, etc. They will talk to you now, so they will listen to you and they will talk to you. And so even more human in this in their input and output devices. So suddenly, computers have memory systems. Some of these memory systems are for long-term storage of information. Some of the memory systems are for information you're currently processing. And so suddenly there were all of these systems that were concrete and imaginable because they were built. They were real things. Some engineer had put this stuff together. And so we could start to think about the computer, and computers became known as information processing devices. And people started to think, that's essentially what we are. We are essentially information processing devices. And so this computer became a very powerful analogy that guided theoretical development, but also kind of made that behaviorist argument feel a little old-fashioned. Like memory? Well, we can have a sense of what memory works. Attention, well, we have raster scans where the computer is looking for input from certain devices. You could imagine that being biased in certain ways. So suddenly people would say, these things aren't so ambiguous. They exist. We can talk about them. We can think about them in very concrete ways. And yes, we can't see them directly. But with clever enough experiments, and this is where the embrace of logical positivism came in, with clever enough experiments, we might be able to learn about them by the traces they leave, so to speak. And I'm going to give you an example of that at the end of this to give you a sense of what I mean by that. Okay, so these computers became powerful. So people started thinking in these terms. And so let me just give you a sense of that. One of those individuals was a guy named George Miller. And he started thinking about channel capacity, or, if you think of bandwidth, right? Like your little Wi-Fi device here needs strong internet bandwidth because that's the sort of amount of information it can receive and send to the internet. So Miller started saying, well, if we are kind of information processing devices, how much information can we handle at a given time? And over time, the thing he was studying came to be known as working memory, or it's kind of consciousness. But he would do things like just give people a list of items, and he would say, keep those in mind as long as you can. And he'd wait a little while, and then he'd say, tell me what I told you. What were those items? And he found data like this, that if you just gave them 1 or 2 items or 3 items or 4 items, they could remember those 4 items, give them back to you fine. If you went to 5, yeah, by and large, people could remember 5 items and give them to you fine. Once you got to 6, you started to see some problems happen. And 7, problems again. 8, even more. 9, very few people can remember all 9 items if you give them 9. And by the time you're at 10, virtually nobody can remember 10 items if you give them 10 items. So he authored something called the magic number 7 plus or minus 2. He had a bit of a sense of humor. So it helped his writing. It made people kind of pay more attention to it. He said, there's the 7 wonders of the world, the 7 days of the week, etc., etc. And it seems like this number 7, this magic number 7, is also part of our mind, that our mind can consider 7 bits of information plus or minus 2. So depending on where you are. So if you really look at this drop, what he's saying is, well, there's some people that can remember 8 or 9, but not a lot. There's quite a few people who can remember 6. So somewhere in this range is what the average person can hold on to in their mind. Okay, and we now think of that as the capacity of working memory. That's what we sometimes call that one. Again, the critical points here is A, this is kind of an interesting thing to know, but B, it is him thinking about our mind as an electronic device that can only process so much information at a time. And so people started doing this, and it started yielding some interesting data. And it started getting people to go, there's something to this. Here's something I just heard the other day. I'm trying to find this study. I hope you guys can help me find it. You know that guy, I don't know if you know this guy, but on CP24 every morning, at least during the COVID crisis, he's coming on and he's giving an update every morning. He's a infectious disease expert. I want to say I want to say his name is Bogart, but it's not Bogart. That's Humphrey Bogart, but Bogash or something like that. He mentioned a study a couple days ago, and I've been trying to find it to tell you guys about it. So maybe you guys can try to find it. But what he described this study where people were asked how rule-abiding they were for COVID. That was one question. So how much do you follow the rules of COVID? But then they were also shown, the way he described it, they went through sort of tests that worked like this. They would be shown a bunch of colors. Let's say, I don't know how many colors. I'm trying to get to the study, but let's say 9 different colors, patches of 9 different colors. And then they would go away, and then not long after they would come back, and you would be asked which colors changed from the first to the second display. And so you have to be able to keep in mind what you just saw and then compare it to what you ultimately see. What they found, what he said, is people who couldn't do this task very well, right? Where you had to keep the number of colors small for them to detect the change. So they would vary the number of colors. That was the notion. And so people who could only see the small number of changes, that once there was too much, they missed it. Those were also the people that were less likely to follow the COVID rules. And so this is a theme of this capacity of working memory, that's the area we use to think and figure things out. And the claim is that some people have a very robust working memory. They can think of a lot of things at once. Other people can only think of a few things at once. And those people who can only think of a few things at once are less likely to follow COVID rules. So the idea being that, if you can logically, rationally think it through, then the rules make sense and you follow them. But if you can't, well, then maybe you rely more on emotion or something like that. Just a fascinating thing to throw in here in the current climate. Okay. He was also big on this notion, just to give you a sense. So this is Miller still we're talking about. These so-called totes. So let me give you a sense. This is how people started to think of the mind doing what we're going to call modular processing, and that you could do a lot with small, simple modular processes. So this is an example of a thermostat, let's say, and let's get a sense. So it has some input on temperature, and it tests the temperature. Let's say we want our temperature 20 degrees. We set it at 20 degrees. Well, it does this test and it says, what's the temperature? And maybe if it's less than, let's say if it's less than 18 or greater than 22, we want to turn either the heat on or the air conditioner on. We want to keep it around 20. So it does a test, and let's say this test says, hey, it's now 16, okay? So it has a rule built in this test that says, okay, if it's 16, send it down there, and keep sending it down there until it's greater than 20, let's say. Okay, and so what it does down there is it turns the heat on. So it goes down and it does something. This test triggers something. In this case, triggers the furnace on. Furnace starts blowing heat everywhere, and it keeps testing, and at some point it says, okay, you know what? It's now greater than whatever we said. 20 or 21 or whatever. So it passes this test and it goes over here and it says, oh, but is it less than 22? Because we want to make sure it's less than 22, right? We want it not cold, but we also want it not hot. And maybe when we did all this, we heated it right up to 24 degrees. And so this test now says, well, is it less than 22? And if no, it's greater than 22, then it kicks in this, which turns on the air conditioner and starts cooling it down. And then eventually it says, is it less than 22? Yes, it passes that test and it goes up, might exit. So anyway, the idea here is you could have these very simple things that just look at it, whether some condition is met or not. And if it is or not, then it kicks on some process and then tests again. And so people got really interested in these so-called tote mechanisms because they were so simple, but when you started chaining them together, you could create systems that could do fairly complex seeming things without need for sort of deep thought or strategies or anything. These simple mechanisms could end up producing powerful, complex behavior. And so they became very enamored with these tote mechanisms. So that's just another example of how, this is almost computer architecture, right? People are starting to think of the mind in these modular ways. Computers are very modular. And so they're following that sort of process and thinking about the brain that way. They're being inspired by the computer. Just other things to think about with Miller, because he was big on both these. First of all, is just this term, subjective behaviorism. He kind of put it out there in jest at first, but it became a rallying cry for a lot of cognitive psychologists. And what they're saying is, we love the methodology of behaviorism. We love the focus on experiments and data and that kind of thing, but we want to bring the mind back. And so that's the subjective part. And in fact, sometimes they used, and Miller was big on this, they used something called the thinking aloud technique, where they would give somebody a problem. Back in the behavior state, right? You just give a problem and you look at the response. But what Miller suggested is, no, just ask the person to think through their response. What are they thinking while they're doing it? So it's not introspection per se, and it's not phenomenology, what pops out at you or whatever. It's just, as you try to figure this out, just speak your thoughts. It sounds kind of weird at first. It shows you some examples in the textbook of speaking aloud protocols, where it shows somebody doing this with the Tower of Hanoi. Check that out. And it's just the person kind of going through what they're thinking and what decisions they're making in their mind. And cognitive psychologists thought, well, you can get a lot out of these. You can get a real sense of what's going on in the person's mind. So that's the subjective behaviorism, that kind of thing thrown out there. All right, so that's Miller. We'll go a little quickly through a couple of these things, but I just want to make this point a little clear. And some of these come from the gray boxes as well. This one does. When you think of a computer, it has input from keyboards. It has input from, well, nowadays, auditory things that can detect your voice. It can have all sorts of inputs. I mean, these suckers have motion detectors and cameras that can be used as inputs, and all sorts of potential input devices. We refer to these in a device as a channel of information. And again, we started to think of human beings in those terms. And so this is a procedure that was used a lot by Donald Broadbent, at least pioneered by Donald Broadbent, called the dichotic listening task, where you would have somebody listening to headphones, but you would have different things being presented to each ear. And so now each ear is considered to be an input channel. And the idea is you can give different inputs to one or not. And now you can tell people to pay attention to one of them. And the way you usually do that, by the way, is to ask them to shadow it, which is to say what they're hearing as they hear it. So as this was going into your ear, you'd be saying President Lincoln often read by the light of the fire, etc. You'd be shadowing this message. Now what we have is an input channel that you're attending to and another input channel that you're not attending to. And so we can look at the effect of attention on things like your memory for what was said, etc. So again, I like this because A, it has that channel notion that we're stealing from computers, right, and engineering in general, and B, it shows how you can't see attention, but you can manipulate it. If you're clever enough, you can come up with conditions where, one situation attention is there and the other one it's not. And then you can look at the results of attention being there or not on, say, memory or other performance measures. And so this was the game that a lot of cognitive psychologists were playing. Stay rigorous to science. Use the computer as a motivation, and be clever in your experimentation. And if you're clever enough, we can learn about the things behaviorists thought we couldn't study scientifically, but we think you can. Okay, so that was another example. As we go through here, just hit a few of these things in general. Jerome Bruner. Why is Jerome Bruner kind of important? A couple of reasons. Let's do the new look first. So the first thing is, and this is almost a little humanism creeping in here, but previous to Bruner, when people talked about perception, the processes of perception, they talked about it as if it was the same for every single human being. that the motives and the lived life of the perceiver did not matter. Jerome says no, they do. And he also thought that the way that perception unfolds can have powerful effects. So let's do this and let's talk about this. So what he's saying here is, okay, let's imagine somebody's coming and you look at them as they approach, and on the basis of a few cues of personal appearance, so they're looking at you and they're just looking at how you appear, but based on very few cues, one categorizes another person as dishonest. I have to read this better. If on the basis of a few cues of personal experience, for example, one categorizes another person as dishonest, it is extremely difficult in most cases to check for other cues that one would predict might be associated with instances of this category. The idea is early on, when you start to see something as something, very early on, and it'll depend a little bit on your history, what you tend to see something as. But once you start to see it as that, it's very difficult to see it as anything else. So there's also the likelihood that available equivocal signals will be distorted to confirm that first impression. So he thought the first impression was critical. So for example, if somebody, as they're beginning to talk, you get the sense they're dishonest, or just walking up, they look shaky to you. You don't get the sense they're going to be honest. Then if they're a little reticent, if they're a little hesitant to give you their views, if you've thought of them as dishonest, you will see that as caginess. They're being cagey, they're hiding things. But if you thought that person was honest, you would see it as more they're being careful to say what they really believe. And so that same hesitancy of speech can be viewed in multiple different ways. And that's just one example he gave. He thought a lot of the things you perceive could be viewed in different ways. And those first ways you view something will shape the whole rest of the way you perceive things. So perception is not just this passive process of the world coming in. It's not even the world coming in being mixed with top-down information like we talked about before, but also what the perceiver is thinking as this is happening will change how this happens. And so a very interactive process of perception that includes attributes of the perceiver. Okay, so he's known as that, and he's got a lot of data that shows that that's true, that these first impressions are critical. He also tried to get at higher order thinking. So things like, how do we ultimately figure out the concepts in our world? Cats, dogs, restaurants, cars, trees, all these things we've learned concepts about. We've kind of learned to categorize them in certain ways. How do we do that? And so he came up with these cards where they would vary on 3 dimensions in this case. Some of his were much more dimensions, but they would vary in shape, they would vary on color, and they would vary on size, right? And so what he would tell people is they would pick one. They'd say, I'm going to pick this one. And he would say, so he would say at the beginning, I'm thinking of a certain category, and it has very specific defining features. And so then I'd say, well, what about this one? And he would say, that's either in the category or it's not. So he might say, yep, that's in the category. Or he might say, nope, it's not. Let's say he says, yes, it does. Well, the category could be triangles. It could be white things. It could be big things. Or it could be big triangles. Or it could be white triangles, etc. So now I have to pick another one to figure out what the category is. All I know so far is this is a good thing. It could be shapes, in which case they would all be yeses. But eventually I would pick one. Let's say I pick this one, and he'd say, no, that's not part of the category. So I'd be like, okay. So it's not just shapes, and it's not just being a triangle, and it's not even being a white triangle, because that won't hold. But it could be being a big triangle. So let me try with this one and see if that's in the category or not. So I would continue to ask questions like this, and then I'd eventually figure out, okay, this is the category. And what he was claiming is we can actually see this process of people forming a category experimentally. So you behaviorists who think we only have to look at stimuli and responses, look at this. This is a much more rich view of the human mind. So again, we see less of the computer stuff in Bruner, but more of that pushback on the limits of behaviorism here. Okay. And the last person I'm going to talk about in this lecture is Sir Frederick Bartlett. Bartlett's very interesting. He was interested in memory. The weird thing about Bartlett, you see, he's actually, sort of played his role a lot earlier, but that's because the English academics were sort of onto cognitive psychology before the Americans, but they were doing it in sort of a small way. And then when the Americans took over, as they make everything big, right? They made everything big, and then they kind of rediscovered what Bartlett was doing. And so Bartlett became big later in his career. The studies he did earlier became important later. And so he did have an effect on this whole cognitive revolution, as it's sometimes called, even though he was actually doing his work before that. The very powerful thing that Bartlett said is that every time we perceive something in the world, we construct it. And when we're remembering something that we previously constructed, we're reconstructing it from the bits we have available. But we have to combine those with other things in order to make it make sense, because the bits are only sort of part of that previous experience. So we have to kind of rebuild it. So let me just give you some idea of what he said. So here's the critical thing that he said. What memory is not is a copy of that previous experience. Unlike the photographs in your camera, our human memory is not just a complete reproduction of something that happened in the past. In fact, it's just bits and pieces of that thing. And we have to rebuild it each time. And that means it might become different each time. And so he wanted to show this process in action. And again, this is part of what the cognitive revolution is all about. The ability to show that you can scientifically get at stuff the behaviorist said you couldn't possibly get at. So here's one of his designs. He starts with this original drawing and he shows it to somebody, and then he puts it away. And then after some period of time, he says, can you please just draw what I showed you? And this is what the person draws. This one, okay? And so now he shows this to the next subject and says, okay, wait a while, and then I would like you to draw it. And then this is what the next subject draws. And then this one gets, so this is like the telephone game, right? This one gets shown to the next subject, a delay is done, and then they draw this, etc., etc., etc. And what you see is that what used to be an owl looking at you, over time, as everybody tries to remember what they saw and reproduce it, they change it a little. And they don't just change it randomly, and this is what Bartlett really showed. They change it in very predictable ways. They do something called normalization. So, this is kind of an exotic owl, and most of us haven't seen owls. This is a pretty normal kitten, and many of us have seen kittens. And so the claim is that over time, people will normalize things. They will interpret what they saw or what they're able to retrieve, and they will make it more like a normal, common part of their life. And so things transform in predictable ways as people recount these experiments. So a very active memory system, one that is very prone to error, because it can reproduce things that weren't part of the original memory. And in fact, if you're really clever, you can maybe make this happen. Let's see if we can make it happen. Memory test. Remember those words at the beginning? Okay, let me show you some. And actually, let's reduce it. Let's go these four. So for each of these four, imagine I ask you the following question. Was watch on the list? Was candle on the list? Was bed on the list? And was needle on the list? So for each of those, I want you to give me a 1 to 5 answer, where 1 is you're sure it was not on the list. 5 is you're sure it was on the list. And then 3 is you're just not sure. Okay? So if I asked you for that, what would you say? Was watch on the list? Give me a number. Was candle on the list? Was bed on the list? And was needle on the list? All right. Watch, candle, bed, needle. Let's go back to the beginning. Ready? I want to show you I'm not pulling any fast ones. So back to the beginning. Was watch on the list? No. So hopefully you said confidently no. Was candle on the list? Yep, there it is. Hopefully you said confidently yes. But here's the cool ones. bed and needle. My prediction is that most of you said, yeah, they were on the list, and that you gave it 4s or 5s, that you felt really confident. Take a look at the list. They ain't there. There's a bunch of things related to bed there. Sleep, pillow, dream, mattress, sheet, night, tired, blanket. There's also a bunch of things related to needle there. Tetanus, stitches, yarn, thimble, cactus, shot, like a shot in the arm, I guess. Pierce, thread, but no needle. Why would you think it was on the list? Well, Bartlett would say you just recreated the list in your mind. And why would you include needle and bed when you recreated the list? Because they really fit. They belong with these other words. In fact, the way we came up with a lot of these words is we started with bed, and we asked people, what's the first word you think of when I say the word bed? And they would say things like sleep, pillow, dream, etc. So these are what we call prime associates of the word bed and prime associates of the word needle. And so when you see those prime associates, it's kind of like the word they all came from is there too. And so when you recreate your memory of the list, you include those items and you feel really confident, even though you just added them afterwards. That is the active processing of the mind. I hope it worked for you, at least for one of those words. I hope one of them you're really confident. We call those false memories. We've created a false memory in your mind of that word appearing. And according to, behavioral psychology, you shouldn't be able to create a false memory that way. But according to this cognitive psychological approach, you can. And you can do so quite easily. Those of you who did Elizabeth Loftus are hopefully seeing a lot of connection here with Elizabeth Loftus, because she really ran with a lot of these ideas and talked about, memory and the way it can be distorted and the impact of that in courtroom kind of testimony. So her work follows very much from Bartlett's original ideas. Okay, that's it for this lecture. I will see you in the second half of this chapter's lectures. All right.